You ever hit a wall with an integral? One of those complex fractions that just laughs at all your usual methods? Well, today we're going to learn how to take those monsters apart, piece by simple piece. This isn't just another technique. Honestly, it's like a puzzle-solving superpower for calculus. So here's our game plan. We're going to start by meeting our impossible integral. Then we'll get into the main idea, which is basically just reverse engineering fractions. After that, we'll look at the blueprint for how to break things down, do a little detective work to find the missing pieces, and then finally integrate everything for the big payoff. And of course, we'll wrap up with the common traps you'll want to avoid. All right, first up, let's introduce the villain of our story today, an integral that just won't budge with any of the basic methods we have in our toolkit. Okay, take a look at this guy. Your first thought might be U substitution, right? That's what most people try. But it's a trap. See, the numerator, 4x plus 1, it's not a multiple of the derivative of the denominator. So what do? You're kind of stuck. And that's exactly why we need a new, way more clever strategy. But you know how it goes. Where there's a villain, there's always a hero. And the hero of this story is actually a super simple idea. Something you probably learned back in middle school. We're just going to look at it backwards. This right here, this is the key to the whole thing. We're not learning some crazy new type of math. We are literally just taking a process we already know, adding fractions, and doing it in reverse. That's it. That's the secret weapon. We all learn this, right? You take a couple of simple fractions, find a common denominator, and smash them together into one, slightly more complicated fraction. We go from simple to complex. And partial fractions, well, it does the exact opposite. It looks at that one messy fraction and asks, hey, what simple pieces did this thing come from? So instead of going from 1/2 plus 1/3 to 5/6, we're going from 5/6 back to 1/2 and 1/3. It's a total deconstruction. And you can see why this is a game changer for calculus. I mean, integrating those two simple pieces is a piece of cake compared to that one big monster. All right, let's keep building on this. Now, to deconstruct a fraction properly, we can't just wing it. We need a blueprint, a set of rules. And it all kicks off with one absolutely critical check. First things first, you gotta classify your fraction. You just look at the highest power of x on the top and compare it to the highest power on the bottom. If the top's power is smaller, you've got a proper fraction and you're all set. If it's the same or even bigger, then it's improper. And this right here is the number one most forgotten step. I mean it. If your fraction is improper, you absolutely positively must do polynomial long division first. That'll split it into a simple polynomial plus a brand new proper fraction. If you skip this step, the rest of the problem is literally unsolvable. Okay, so this table, this is your master blueprint. Once your fraction is proper, you factor the denominator completely and just match the pieces to this guide. Let's walk through it. Case 1, you've got simple different linear factors like x minus a and x minus b. Each one gets its own simple fraction with some unknown like a or b on top. Easy enough. Case 2. A repeated linear factor, like x minus a squared. This one's a bit tricky. You need a term for every single power up to the one you have. So, one for x minus a and another for x minus a squared. And finally, case 3. You have a quadratic that you just can't factor any further. Well, its numerator is going to be a linear term, bx plus c. That's it. You just follow the template for whatever factors you end up with. So, once we have our blueprint all set up, we've basically turned our one big fraction into a sum of smaller pieces, but with these unknown numerators, a, b, c, and so on. So now it's time to put on our detective hats and figure out what those constants actually are. We've got two main tools for this investigation. The first one is a really clever shortcut, sometimes called the cover-up rule. It works great for distinct linear factors, like in our first problem. You just plug in the roots of the factors, like x equals 2, and it magically makes other terms disappear, letting you solve for a constant instantly. It's super fast. The second tool is the universal powerhouse, equating coefficients. You multiply everything out, group all the x squared terms, all the x terms, and so on, and then you match them up on both sides of the equation. Yeah, it's more algebra, but this method is a fail-safe. It will work for every single case guaranteed. And now we get to the whole point of this entire journey. After all that algebraic heavy lifting, our so-called impossible integral has been transformed. It's now just a simple sum of integrals that, honestly, are pretty easy to solve. This, right here, is the payoff. So here's the cool part.
No matter how complicated the original problem was, your broken down pieces will always integrate into one of these three forms. That's it. A simple linear factor in the denominator, that's going to give you a natural log. A repeated linear factor, that's just the plain old power rule. And that irreducible quadratic, it will always break down into a combination of a natural log and an inverse tangent, or arctan. And just like that, the problem is solved.
Okay, before we wrap this up, let's talk about the most common mistakes. Mastering any new skill isn't just about knowing what to do. It's about knowing where the traps are so you can sidestep them. These are the big four. Number one, we've said it before, but forgetting long division for improper fractions. It's a killer. Number two is thinking everything turns into a natural log. Remember, those repeated factors use the power rule. Number three is a classic, forgetting the absolute value bars inside the logarithm. And finally, number four, when you integrate something like 1 over 3x plus 2, don't forget that reverse chain rule spits out a factor of 1/3 in the front. Steer clear of these four, and you're going to be in great shape. So you might be thinking, is this just some abstract thing for a math test? And the answer is a hard no. This exact technique is a fundamental building block in all sorts of higher-level science and engineering. It's essential for things like inverse Laplace transforms, which are used to solve the really complex differential equations that model electrical circuits, mechanical systems, you name it. When you get right down to it, partial fractions teaches us a really powerful lesson, right? It shows that a problem that seems impossibly complicated is often just a bunch of simple problems wearing a disguise. The key isn't to use brute force, but to find the right framework to just break it down. So it makes you wonder, what other impossible challenges out there are just puzzles waiting for us to find the right tool?